The story goes this way. Here's the engine. I make sure I did the right drawing last night. And the engine is a closed system. This square is defined by an impermeable boundary. And the engine is in contact with the two regions, one warmer than the other. And then into this closed system flows a heat current called QH, and this time I mean joules. And this engine, of course, operates in cycles, meaning cycles means the state of what's inside the box does not change over time. If the cycles are very many per unit time, then this is known as a closed system operating in steady state. And the engine produces work, a number of joules. Work is force times displacement, meaning this W is used for the purpose of pushing something to a distance. And then the difference between these two arrows, I draw a smaller arrow, is called the heat current rejected to the ambient being the lower temperature. So this is the beginning of the argument, meaning what led to thermodynamics was the demonstration by imagining a particular design. One, I mentioned the cylinder, the piston, and the in and out happening at a slow enough rate or speed such that shocks were avoided, turbulence was avoided. Anyway, it's called quasi-static operation. In that limit, which is known as the reversible limit, the work output from the difference between these two arrows is the greatest that it can be, namely the heat input times what's known as the Carnot efficiency, TL over TH. So that's the known as the Carnot work. And comparing any engine with the Carnot engine, the observation, or the let's call it proclamation, is that any engine is cursed or destined to produce less work than the Carnot engine. In this particular comparison, the imperfection is evident. It is the fact that the mortal engine, by the way, the reversible engine is an object of the imagination. All engines are, to a large or tiny extent, irreversible. The comparison declares this, real engine as imperfect. The other word for perfect is ideal. That's a description of the Carnot engine. The imperfection can be measured as the difference between what you could obtain in principle from burning this much fuel. So imperfection is the difference WC minus W. And all the research and development that goes on in power power plants and motorist engines and other things today and in history is about ways to reduce this difference while at the same time trying to reduce the expenditure of the effort of reducing, and also the weight of the engine that has to be carried on a vehicle that obviously burns fuel. Engine doesn't exist by itself. Engine travels with the object that the engine's work is pushing, you see. And from this, so here I'm putting my fingers on a problem we'll solve together a little later in the course. The fact that organs do not happen alone. They are not born alone. Organs alone. Textbooks alone, forget. There's an E after alone, am I right? Thank you. Textbooks teach that way, but organs do not happen by themselves. Organs on movers. I mentioned the muscle mass on the animal, organ, lung on the animal, heart and so on the animal in motion. And this view is holistic. Another way of fighting against reductionism, you see. Because if you buy the idea that you understand the animal if you know the organ, that means you'll understand the organ if you know the red blood cells, a single one, and then you understand the red blood cell if you know what's inside that particular organism called a cell, and so on. It's true, but not complete. The holistic way is the way of engineering. All right, I'll come back to the imperfection of thermodynamics because the older versions of imperfection will shed light on how big or small this penalty can be. And let's look at fluid mechanics or fluid flow. The simplest way, fluid flow is of two kinds. It is something that flows while embraced by a wall, such as water flowing through a tube. That is known as internal flow. The other story is just like in Aristotle's statement. The other extreme is called external flow. Where, unlike in the internal flow, where the solid wall envelops the fluid, in external flow, the flow envelops the solid wall. The flow around the wing of the airplane is external. The flow, that's air. Water flow around the boat, the boat with outboard motor, that's an external flow. It's the same kind of flow. So that's why this asymptote is important by itself, and the other one the same, important by itself. Anyway, here's the internal flow, sketched inside a tube. The tube has a cross-section called A. It doesn't have to be round, it could be any. Get it? A means area, also means the word any. By the way, any is the most powerful, shortest word in science. Yes, any. Name your child that way, then this person will become the new Napoleon. Very powerful word. If you know what's good for any, you really know stuff, okay? And the cross-section has a perimeter P. And the flow, that of course is conserved, m dot means kilograms per second. Imagine air or water flowing through a duct. And of course, what I drew is a solid surface. That's the wetted surface of the duct, also known as control volume in thermodynamics. This picture would be a description of reality, provided that there's a pressure difference, delta P, between inlet and outlet. And now you put yourselves in the shoes of Adrian. When I was your age, I said, hey, wait a minute. Here's a box. I drew it as a cylinder that's being pushed from the left by a force. The force is pressure difference times A. Yeah. What about it? It's a puzzle or a conundrum because the box is not moving. Where's the other force that balances this one? And this is how you discover that delta P happens or is necessary because of friction all along the wetted surfaces. And this little arrow is called tau, or skin friction, a quantity, the units of which is force per unit area, meaning Newton per meter squared. And so true, or yes, thank you for asking the question, there is another force that balances the first, and this second force is tau, integrated over the wetted surface, which is P times L, where L is the length of the tube. All right. The units here are meter squared. This is Newton per meter squared. Same here, Newton per meter squared. And these two meters squared. So I'm checking, making sure that I did not forget a factor in this equality, or balance of two forces. And once recognized, this balance allows you to figure out the pressure difference that the pump upstream of the duct must provide, must maintain. So the pressure difference is tau P L over A. In these older disciplines in which calculus propagated, I'm talking about fluid mechanics and heat transfer, people like to found it convenient and actually very useful to non-dimensionalize things. So for tau, the quantity that was invented as the dimensionless tau is called the friction factor, which is tau divided by a group that has the units of pressure, where U is the average speed of the flow. In other words, what I'm writing on the blackboard is for any flow regime, laminar or turbulent, boundary layer, doesn't matter. It's general. And regardless of regime, if you average the flow velocity distribution over the cross-section, you obtain the average speed of this fluid through that cross-section called A. The name for that is U. The definition of it, the definition of U is mass flow rate divided by rho and then cross-sectional area. So that's one definition for capital U. This is another definition for tau. And when you substitute everything in this delta P expression, you get delta P equals friction factor, and then PL over A, and then 1/2 rho U squared. Furthermore, and this is a review of things you know from fluid mechanics, it was replaced by, so what was PL over A in the literature became 4L over V sub H, where V sub H is the hydraulic diameter, defined as 4A over P. Obviously, a quantity with units of meter. And the reason why this hydraulic diameter was invented is that not all the ducts are round. And the name diameter for this group was chosen such that in the special case of a round duct, then 4 times the area is pi radius squared. The perimeter is 2 pi r. You get 2r, which is the diameter of the round pipe. Okay, so that means that any duct is a round pipe that's been dented from the sides, okay? And now you're going to experience Adrian's goosebumps when I was your age. I asked myself, yes, you can calculate the hydraulic diameter for anything. For example, for the duct with a square cross section, you can calculate it. But what about the drawing? What is this imaginary round pipe with the diameter called hydraulic diameter? But after you calculate dH for the square, you find out that the hydraulic diameter is the diameter of the circle inscribed in this regular polygon with 4 sides. Goosebumps. Well, if that's the case, what about the equilateral triangle? You can calculate dH, make the drawing, and discover the same thing, that the hydraulic diameter of this cross-section, which is even more dented from the sides, appears to be smaller, you see. In other words, the flow, which has a mind of its own, chooses, just like the thread of the water, the thread of the river. You know, the river doesn't flow at uniform velocity downstream. The river flows with high velocity as a thread that only the pilot on the boat knows. All right. The thread of flow through this cross-section is through the hydraulic diameter, not through the corners. Sharp corners pinch the flow. Sharp corners are the reason why flow through ducts encounter resistance. You know already to expect a smaller resistance to flow through a square duct. An even smaller resistance to flow through a hexagonal cross-section, where the hydraulic diameter indicates that the hexagon is even closer to being a round duct. But in this direction of increasing the number of sides to the regular polygon, you see one more time why the hydraulic diameter of the round tube is the same as the diameter of the tube. But to every aha, there is an yes, but, ... comment, which also came from me. What about a duct that's really, really, really hammered from the sides? And that is the slit. So the flow is into the blackboard. Meaning this is a two-dimensional opening, an opening with a spacing called D. Meaning much, much wider the opening than it is measured across. You can calculate the hydraulic diameter, and it is this. Twice, so DH for the slit is twice the spacing. This is the anomaly, or for that matter, all such, let's call them oval-shaped cross-sections proceeding from this one to this one will have hydraulic diameters greater than the spacing, greater than D. Maybe I spent too much on this. And that leads to the final formula for the pressure drop, which is the friction factor, and then 4L over hydraulic diameter times this artificial pressure unit called is basically dynamic pressure head, rho U squared. So this formula is general. But the formula for the friction factor depends on the flow regime. Laminar, turbulent, and something more complicated in between. These are steps I skip because you have them in your fluid mechanics book. Oh, and now, where is the imperfection? Remember, imperfection is negative. It's something to avoid. What's your problem when it comes to flow of a fluid through a duct? The imperfection is in your pocket because, and I erased, I did not erase, I did say that this delta P has to be maintained by a pump. So upstream is a pump. In other words, the complete picture, speaking of holism, is not the organ called the duct that I drew there. It is the pump connected to the duct together. That is the so-called system. And I'll draw it here. Here's the duct. I'll make it smaller. And this flow goes in, m dot, with delta P. It goes out, m dot, and there's a circuit maintained by the pump. I'll say lowercase p, this way. And the pump is doing this work of forcing the flow through this narrow opening. Fluid flow is not stupid, would not flow through a narrow space unless pushed. As a matter of fact, nothing moves unless it is pushed. Why is the flow happening? It's because of you. You purchase power, you draw it from not this outlet, because here you get it for free, but in real life you have to pay for the electricity that drives the motor or that drives the pump. So this is called power to the pump, which is a number of watts. So the imperfection is the fact that you have to spend power. You pay for it. And once the motor that produces this power runs and delivers the power, that power is destroyed instantly. It is not saved somewhere. Everything that moves because it is pushed destroys the power that pushes it. So this is the loss. I'll put the dollar signs here. And the power requirement of a pump, this is from Thermodynamics. You can show this quite easily. It's the product of mass flow rate times pressure difference divided by the density of the fluid, and the so-called pump isentropic efficiency, which is a number comparable with 1, very close to 1. So you might as well not think about it. So mass flow rate is something that the people tell you that you need, say in the blood circulation, you need so much flow rate to deliver so much oxygen to the muscles during effort, and on and on. But the pressure difference is something that for which your body has to pay with everything from food and other pieces of the very complicated design of the animal body. So this is lost because of the delta P. Before I continue, this drawing is incomplete. If it were true, once again, holism, always imagine the object of your inquiry, imagine it inside a control volume. And then, in your head, to that control volume, invoke the laws of thermodynamics. So here's the control volume. It is an open system. It's actually a closed system. No mass is leaking out of it. Operating in steady state. And you're pumping watts into it steadily. If this box, if this drawing were to be accurate, then the box would be accumulating energy, meaning it would not be operating in steady state. But it is in steady state because everything that I sketched is surrounded by the ambient, and so the control volume is leaking heat to the ambient at the same rate that you're pumping work into it. Get it? This is important to keep in mind. The work that the engine produces, that work is necessary to move things, that work is instantly dissipated into heat to the ambient by the mover that rubs against and gets the environment out of the way. A joke goes with it, and I'll get to that in a second. I go here, This is the first formula in which we get a formula for imperfection. Imperfection, which is here, is proportional to a current. I call this m dot a through thing, something that electric current, fluid flow current. That's for current. Times a measurement that you do across between the beginning, the inlet and the outlet. So that's across is the, you can call it the delta P. In electricity is called the voltage. In, say, a sack of potatoes being dropped from the balcony is the height. The through is the sack that moves from high to low. The loss is the gravitational potential energy of that sack. Get it? It takes two to have imperfection. This one goes this way. The other one is measured. Well, sorry. The other way is measured from end to end. And this is the image. The tango, the tandem of through and across that accompanies every claim of imperfection in a moving system. Remember, there were three disciplines in which I was illustrating the physical meaning of imperfection. Those were thermodynamics, and then fluid mechanics, and then heat transfer. So I took care of this. Heat transfer turns out to be even easier now that we know what we're talking about. Here's a piece of something. Go back to the fundamental brick. Say it's around the brick is separating the fire, the furnace, from the room. So the fire is here, and through the brick there's a current of heat leaking to the ambient. The flow is unidirectional. The heat, the arrow, it's called heat transfer rate, is conserved. In other words, this square box as a closed system in steady state reaffirms the correctness of the first law of thermodynamics. From that point of view, the fact that Q dot is conserved, where is the imperfection? There's no loss in the discipline of heat transfer. Of course there is loss. And here it is. Every time you have something that flows from high to low, in this case from TH to TL, which means one-way flow, the hint is that I'm going to do to heat transfer what I did here for fluid flow. This is from high to low. Every time that happens, you lose the opportunity of having that flow go the other way. Gone means gone forever. It doesn't come back by itself, unless it is vehicled back through the expenditure of power. That's a longer story. So what is the loss? That has to do with the irreversibility, now thermodynamic speech, of heat from high to low. The loss is, and just the other day, people celebrated 200 years since the memoir of Sadiq Carnot, is that this box I drew earlier, with the same temperature difference and the same heat input, could have been producing in steady state power at the rate prescribed or predicted by Carnot. So if this is a Carnot engine, then the power here would be that, and I write the formula down here, Q dot H Q dot H times 1 minus the Carnot efficiency. So that's the power. The power that was not collected from the same apparatus, the same object, because its guts were not engineered, not designed the way that, in principle, they could have been. How big is this lost power? Well, it is Q dot times TH minus TL divided by TH. So this is the loss associated with heat transfer. Why is it big? It is big because the product between the through and the across, this is the across, is big. So once made this discovery, it reappears. This is because now your imagination is cannot be fooled anymore. It's powerful. That discovery is discovered time and time again because you know what to expect.